Good afternoon, everyone. Today I'm going to talk about the computer assembly language. I use some recordings from my previous years for some slides. Okay, so just for an introduction, as you know, embedded systems are being used in many places, smartphones, in your automobiles, robots, and so on, as you see in this slide. So, and we want to have a high performance embedded systems. We need to just use assembly programming. Not only we want to improve the performance, but for the having a low cost implementation, we need the assembly programming.
Let me briefly summarize why we should learn another assembly language. In fact, assembly language is not just another language. It would help you understand how the processor works. When we compare two programming languages of low-level assembly language with a high-level language such as the C programming language, we conclude that the assembly program runs faster than high-level language. As a result, performance-critical codes may need to be written in assembly. Sometimes we use the profiling tools to analyze the execution time of each section in a complex code written in high-level programming language. Then we find the performance bottleneck and so rewrite that code section in assembly. For latency-sensitive applications such as aircraft controller and anti-lock brake system or ABS, the code should be written in assembly in order to have a very low latency execution time. Nobody wants the ABS processor in our car has a high latency after we press the brake pedal. On the other hand, we don't care about the latency of a microcontroller in our dishwasher. Standard C compilers do not use some operations available on ARM processors, such as ROR, rotate right, and RRX, rotate right extended. As a result, if we need to perform such rotate operations in C, we should use several C instructions, and so the overall execution time and code size will be greater than the ones using the ARM assembly. The codes for hardware and processor-specific applications should be written in assembly. These codes include processor booting code and the codes using device drivers, compiler, assembler, and linker. For cost-sensitive applications, writing the code in assembly helps us reduce the code size. These applications include embedded devices where the size of code is limited, such as Internet of Things devices, IoT, washing machine controller, and automobile controllers. Finally, learning assembly language helps us better understand high-level programming languages. Why do we choose ARM processor for this course? Obviously, it's a good name because my name is ARM, Arash Reyhani Masule. The name ARM for the ARM processor came from Akron RISC machine. The ARM processor is a RISC processor. A RISC or reduced instruction set computer is a type of microprocessor architecture that utilizes reduced instruction set. Let me define instruction set. An instruction set is the entire collection of instructions for a given processor. Let me briefly talk about the first RISC architecture. The first prototype computer to use RISC architecture was designed by IBM researcher John Koch and his team in the late 1970s. For his efforts, Koch received many awards and medals, including the prestigious Turing Award in 1987. The Turing Award is often referred to as the computer science equivalent of the Nobel Prize. RISC generally refers to as a streamlined version of its predecessor, the CISC, Complex Instruction Set Computer. Let me briefly compare these two computer architectures. The RISC architectures have a small number of fixed-length instructions, whereas the CISC architectures have large number of variable-length instructions. As a result, these computers have simple, uniform, and standardized instruction formats, whereas the CISC computers have complex and variable-length instruction formats. As a result of having fixed-length instruction in RISC architectures, each instruction in RISC architectures is executed in a single cycle, which is good for pipelining. On the other hand, since each instruction in CISC architectures has a variable-length instruction code, the number of execution cycles for each instruction varies depending on the instruction. The RISC architectures have limited addressing modes in their instructions, whereas the CISC architectures have more and compound addressing modes. We will talk about the addressing modes of the ARM processor later on in this course. RISC architectures with a small number of instructions requires more memory for the code as compared with CISC architectures. Memory is cheap these days, and designing RISC-based systems became more attractive. On the other hand, the initial idea behind the CISC architectures in 1970s was to emphasize on hardware in order to have a smaller code size. At that time, memory was expensive. As examples of instruction, the RISC architectures contain register-to-register instructions, load, which is defined as a data transfer memory from the memory to the register, and the store, which is defined as a data transfer from register to memory. Operations are independent instructions. On the other hand, the CISC architectures have memory-to-memory instructions. Load and store operations are incorporated in instructions. Our main reason for choosing the ARM processor is because it has been used in many products and systems. In 2010 alone, 6.1 billion ARM-based processors have been manufactured, representing 95% of smartphones, 35% of digital TVs and set-top boxes, and 10% of mobile computers. As of 2019, 150 billion ARM processors have been produced.